Hello and welcome to our webinar. My name is Peter Simon. I'm Product Manager at QATM in the headquarters in Germany. I'm very pleased that you participate to this webinar. Today's webinar is about efficient planar grinding of metallographic samples.
Hello and welcome from my side. My name is Parham Magami. I'm working as lab manager in Germany, Mamelzon. Today I will show you some applications examples from the planar grinding.
The webinar will last about 40 minutes. During the webinar, you have the possibility to ask questions using the chat function. We will try to answer your questions shortly. First, I want to give you a rough overview of today's webinar. In the first point, we will deal with the question of why plane grinding is important. I will present the three typical goals of metallographic plane grinding, and my colleague Parham will present application examples. In the second point, I will go into more detail about the grinding process with the grinding stone and present a series of tests with different influencing factors in the grinding process. I will show you what effects these have on the surface quality and the removal rate. Here I will present application examples with different materials too. Let's start with the first point. Why is plane grinding done? In the run-up to Christmas, I had the idea to illustrate this with an apple. On the left, you can see the first default application. The apple is often peeled and then processed in the kitchen. I also often want to grind my metallographic sample flat to prepare it for the next preparation steps. This can be plane grinding a single sample or a sample holder at one level in order to be able to achieve good results in the subsequent grinding and polishing steps. Another goal of plane grinding is the removal of artifacts such as deformation zones or very rough surfaces. In the case of an apple, that is not so tasty. Deformation zones are often cut out in order to be able to enjoy the undamaged apple. Even in metallographic samples, these deformations are often unacceptable in the desired analysis and must therefore be removed beforehand. The third goal of metallographic plane grinding is to achieve a desired preparation target. In this process, the sample is ground down to a defined dimension in order to be able to carry out an analysis of the material in the middle of the sample, for example. I have shown this third goal of plane grinding here with a halved apple. If we take a closer look at plane grinding as preparation for subsequent grinding steps in laboratory practice, we often find mounted samples that are clamped in the same sample holder and need to be ground flat. Very often we prepare 6 samples, 8 samples, or 12 samples at once. It can also be very large samples that need to be ground flat. In addition, there are unmounted samples or sample packages in which a large number of samples can be prepared at once. Before the samples can be ground automatically, they must be fixed in a sample holder. When clamping the samples, care should be taken to ensure that the samples are clamped as flat as possible. The fixation with the screws can cause the samples to tilt slightly. There are tools to minimize this effect. On the one hand, there are leveling discs. You can see it on the left side. And with this leveling disc, it's possible to clamp your samples to a defined plane. On the right side, you can see a leveling device that can be used to press the samples onto the leveling disc um, with a pneumatic punch and then fix it with the screw. Now the first sample is clamped, and so the whole sample holder can be aligned to one plane. At this point, I would like to point out two things. First, I would like to underline that with a well-leveled sample holder, the grinding time can be significantly reduced. Second, I would like to recommend that by carefully deburring the samples after cutting or even after mounting, the samples can be leveled much better and the grinding time can also be shortened.
Here we will show you an application example. The customer wants to prepare a high amount of hot rolled steel samples, and here the task is to prepare them till 1 micron. The aim of the investigation is to analyze the microstructure and determine the grain size as well as examine the oxide layer. We were able to clamp the samples in sample packages with 3 to 4 cuts clamped on top of each other. This allowed us to load the sample holder with 19 samples at the same time. We ground this sample holder with a 100 grit aluminum oxide grinding stone at the standard speed of 1500 RPM and the grinding stone at 120 RPM on the head. The pressure was set at 180 newtons and the sample holder was ground planar within 2 minutes. On the right side, you can see how the sample packages looks like, as well as the microstructure after 1 micrometer polishing and etching with 3% alcoholic nitric acid.
Now let's move on the second goal of the plane grinding, the removal of deformed material. It can be an unevenness of the sample through the cutting process. On the right side, you can see a roughly separated sample that was made manually in a shop cut. It is a steel sample C45. You can see the coarse surface and also a burr from the cutting process. These artifacts must be removed by plane grinding in order to eliminate any changed material structure. This changed structure can also be caused by heat input during the cutting process with incorrect parameters. On the left side, you can see a hot mounted sample in epoxy resin. During mounting, the resin has run under the sample, so that the excess mounting resin must be removed first. Even with cold mounted samples, it can happen that that the sample surface is not flat, but somewhat concave or convex. Here, the mounting material must be removed too. In principle, it is recommended to use a suitable wet cutting process with a suitable cutting wheel, a cooling system, and the right cutting parameters. The use of a suitable clamping tool can also help to avoid burrs and those also reduce the plane grinding time.
Here is an example of removing deformed surfaces. We have 3 samples of martensic steel with a hardness of 60 Rockwell C. These steel samples are mounted and have a size of 100 to 50 millimeters. The objective of the investigation is to remove 1 millimeter to remove the deformations on the cutting surface. Then a preparation down to 1 micron should take place, followed by microstructure analysis and also hardness testing on the edge and core of the sample. Surface grinding was carried out with an aluminum oxide grinding stone and the standard rotational speed and a pressure of 200 Newton. Despite the high hardness, a removal rate of 1 millimeter could be achieved in just 5 minutes. The ground surface can be seen on the right side. After polishing, in the polishing steps of 9 micron, 3 micron, and 1 micrometer, etching was performed with 3% alcoholic nitric acid. Here the objective is to investigate the microstructure and do the hardness testing. As you can see in the middle of the page, the microstructure before the etching and also the oxide layer on the edge of the sample can be seen. And on the right side, you can see the microstructure, the martensite microstructure after etching. Here is an example for planar grinding of the nitriding layer. As you can see on the left side, 6 samples of the nitrided gear wheels can be prepared simultaneously. The problem here is the breakouts of the nitride layer during the cutting, and the objective is to ground the samples to the middle of the gear wheels and then perform the nitriding hardness steps on the sample. The aluminum oxide grinding stone with the grit of 100 here can be used, and also the rotational speed of the head and of the stone can be as usual 1500 for the stone and 120 for the sample holder. And also 170 Newton pressure can be also performed. In this case, 2 millimeter removal rate can be achieved in 6 minutes, and after polishing down to 3 microns, you can see the microstructures and also nitriding layer on the right side. As you can see here, the aluminum foil was used to protect the nitriding layer on the edge of the sample. And as you can see on the right corner, the aluminum foil can be protect also the nitriding layer, and the sample can be prepared without any problem, and also the grinding can be done also without any problem.
Now we want to talk about the third main application of plane grinding to a target plane. The goal is to achieve accurate material removal in the shortest possible time. Examples for this are, for example, weld seams, screws, balls, or wires, which are mounted and ground down to the middle of the sample. With the help of grinding, the cutting of the samples can be omitted and the desired target level can be achieved very precisely.
In this example, steel wire segments with a diameter of 12.5 millimeters were to be ground to the center. The 12.5 millimeter steel wires were mounted in a sample diameter of 50 millimeters. The aim of the investigation was to grind and polish to the center of the sample and then examine microstructure and perform a case hardness depth hardness measurements. 3 samples were ground simultaneously in a sample holder with a contact force of 150 newtons. The removal rate of 6 millimeters was achieved after 7 minutes. On the right side, you can see the ground surface of the samples in the sample holder. After preparation down to 1 micron, the hardness test could take place, and after etching with 3% nitric acid, the microstructure can be investigated under optical microscope. Now we have a brief overview of the topic of why planar grinding is used at all. We would like to move on to the second point, planar grinding in metallography. Basically, they are different ways to grind a sample flat. On the very left side, you can see a conventional method in which a pre-grinder is used to grind individual samples completely flat by hand. Next, you will see a method familiar to any metallographer, conventional surface grinding of a single sample on a grinding polishing machine. Abrasive paper as well as diamond grinding disc can be used here. Automatic grinding with a grinding and polishing head makes it possible to grind several samples at the same time. As you can see here, this can be ground in single or central pressure. As this process runs automatically and the grinding force no longer to be applied manually, longer grinding processes with higher material removal can also take place. Here the reproducibility increases as well. On the right-hand side, you can see the process that I would like to explain to you below, the stone grinding. In this process, the sample throughput increases, the material removal can be determined very precisely, and high forces also ensure the very high removal rates. Corundum, aluminum oxide, or silicon carbide grinding stones are generally used here, which have an incomparably long service life compared to sandpapers.
How is a stone grinding machine designed? It has a very stable and low vibration machine design. Powerful drives drive both the stone and the polishing head. During the grinding process, the force is electronically controlled and the removal measurement system measures the material removal. An integrated cooling system is necessary for the grinding process. The process is controlled and monitored by control software. The advantages of stone grinding are the high cutting speeds of up to 2000 RPM on the grinding stone. As a result, a very high material removal can be achieved. And a grinding stone has a significantly longer service life than other grinding media. High grinding forces of up to 750 newtons can be applied. A very precise removal measuring system is integrated, and the robust design allows both a very flat grinding surface and high removal rate. Here I have prepared a sketch to highlight some influencing factors in the grinding process. An important factor is the material that is to be ground. Not only the material itself, but also the mounting resin should be taken into account. Some mounting resins are suitable for stone grinding, others are not suitable. Another important factor is the grinding force, which can be applied on the sample holder. The speeds for the sample holder and the grinding stone can also be changed and influence the grinding process. Cooling also plays a very important role. Due to the high cutting speeds and forces, both the sample and the grinding stone must be cooled. Modern grinding machines are therefore equipped with a coolant monitoring to ensure that there is always enough cooling water in the grinding process. On the left side, you can see the dresser. All stones must be dressed with a diamond dresser. In this dressing process, the dressing depth and the dressing speed can be changed, which also has a major influence on the grinding process. After all, there are different stones and different applications which also have a significant influence on the grinding process. If we look at the grinding process in detail, let us talk about this illustration. The abrasive grain, which is embedded in the grinding stone, slides over the sample material. It moves from left to right across the sample surface and penetrates the material with a certain relatively speed and a contact force. The grain first deforms the material elastically and then plastically. Through a process called microplugging, material is displaced to the sides. The grain then begins to separate a chip from the material, creating material removal. The geometry of the abrasive grain also plays a role in the chip volume and the material removal. The smaller the rake angle of the abrasive grain, the greater the chip volume and the material removal. The cutting rake angle of my abrasive grain can be changed only by dressing the stone. Therefore, the dressing process is very important. On this slide, I want to talk about the stone as an influencing factor. 3 different abrasive media can be used on a plane grinding machine. Ceramic bonded corundum stones are most commonly used, which are suitable for tool steels, stainless steel, and cast iron. Silicon carbide stones are mainly used for sintered materials and non-ferrous materials. For special applications, there are also diamond grinding wheels with resin bonds, which can be used for very hard materials such as ceramics or tungsten carbide. As a machine manufacturer, we have the option of defining different recipes for our stones. We vary the grain sizes from P80 to P150 and realize different bond hardnesses and porosities, which have an impact on the removal rate and the service quality of the samples.
I would like also to briefly show you an example of an application with non-ferrous metals. Here we have a large medium strength titanium alloy, titanium aluminium vanadium Tc4 alloy. The sample is relatively large, 140 to 100 millimeters. The aim of the investigation was to prepare the entire sample without additional cutting and to carry out a microstructural analysis. This sample was ground with the SiC grinding stone with a grit size of P150. A pressure of 125 Newton was applied and the sample was ground planar in just 90 seconds. On the right-hand side, you can see the conventional microstructure of the alpha-beta titanium alloy after etching with Kroll.
Now we come to the dressing process. When is the right time to dress the stone? In the past, you had to find the right time for dressing by hearing, seeing, feeling, and measuring. In fact, if you stand next to the machine, you can hear whether there is material removal or not. An experienced user can feel the stone and tell the difference whether the stone is sharp or not. Modern grinding machines have an integrated system that can display the material removal. If you look at the grinding process as a user, you can see very clearly how high is the current material removal in the process. Based on the diagram, it is not so difficult to choose the right time to dress the grinding stone. After the stone has been dressed, you can very clearly observe how the material removal increases again in the grinding process. Nowadays, this evaluation is done by the machine itself. In this case, shown here, the machine automatically dresses the stone when the material removal is halved by 50%. If you look at the stone with microscope, you can clearly see the difference between a sharp stone with sharp abrasive grains and a blunt stone with matte stone surface. Even with your eyes, you can distinguish between a blunt stone and a sharp stone. If you grind your sample holders with a blunt stone, you will have low material removal, heat generation, and uneven sample holders. This should be avoided. Now I want to show you the grinding process in a modern grinding machine. Here the machine is grinding the sample holder. On the left side you can see the dresser, and on the right side you can see the grinding process displayed in the software. The removal rate is going down, and the machine is evaluating the removal rate, and then the dresser automatically dresses the stone when the removal rate is down to 75%. After the grinding process, we have a cleaning process with spinning the sample holder, going to the cleaning station, cleaning the sample holder with high pressure water pressure, compressed air, and ethanol. After the cleaning, you can remove the sample holder from the machine and go to further grinding and polishing steps. Another influencing factor is the dressing speed. This is the speed at which the diamond dresser dresses the stone. If you dress the stone with a high speed, a spiral texture is created on your stone surface. This rough stone surface creates high removal rate, but also a rough sample surface. Is the stone dressed very slowly? The stone has a smooth surface and also produces a smooth surface quality on your samples. However, the removal rate is low with the slowly dressed stone. In technical jargon, a distinction is made between roughing and finishing. To illustrate the influence of dressing speed, I started a series of experiments and tested different dressing speeds. As sample material, I have chosen a C45 standard steel with a diameter of 50 millimeter and a hardness of 180 HV. I started with standard parameters and a constant grinding force of 250 newtons to achieve material removal of 1 millimeter. The average removal rate, the surface quality of my samples, and the micrographs of my samples were evaluated to see the influence of the dressing speed. I ground the sample holders at different dressing speeds in the roughing, normal grinding, finishing, and fine finishing mode. At different dressing speeds, I was able to see a big difference in the grinding time and the dressing rate. In the roughing mode, the grinding time can be reduced by 50% compared to the fine finishing mode. I could also see that when the grinding stone is roughly dressed in the roughing mode, the number of dressing processes is significantly lower than in the fine finishing mode. The influence on the surface quality is also big. If you look at the ground surfaces under the microscope, you can observe increasing quality from the left to the right side, which is also confirmed with the surface quality in micron. If these results are displayed in a diagram, a linear relationship between the removal rate and the surface quality can be seen. In the roughing mode, the removal rate is very high, while the surface quality is very rough with a value of 0.9 micron. Slower dressing speeds affect both the removal rate and the surface quality. On the right diagram, you can see that very fine dressed stones, the stone consumption increases the factor of 3. This is because a fine dressed stone clogs up more quickly and therefore has to be redressed more often. The dressing speed therefore has a big influence on the removal rate, the surface quality, and the consumption of the grinding stone. In the second attempt, I worked with the same sample holder and the same grinding parameters, but always in the roughing mode and with the fast dressing speed. I only changed the dressing depth. The dressing depth is the measure of how deep the dresser penetrates the grinding stone during dressing. In the grinding process with stones, dressing depths of 5 micron to 30 micron are recommended. Therefore, I choose this area for my series of experiments and ground my sample holder with these different dressing depths. Here we can see our results. The dressing depth has a significant influence on the removal rate and the surface quality. If I choose a dressing depth of only 5 micron, I have a low material removal, but a higher surface quality. From a dressing depth of 20 micron, I was able to achieve a maximum removal rate for my application with my standard steel C45. Since the dressing depth is also directly related to the stoneware, I was able to decide easily that the dressing depth of 20 micron is the best for my sample material and my sample size. In the last two experiments, we focused on the parameters that you are probably most familiar with. In the third experiment, I tested different grinding forces and measured their impact in the grinding process. The experiment conditions were the same as before, but I always worked in the roughing mode and choose a dressing depth of 20 micron. The grinding force is the force in the process in which the sample holder is pressed on the grinding stone and the grinding grain penetrates the base material. I set this grinding force between 150 and 400 Newton, thus creating different surface pressures on my sample with the constant sample area. Here too, the results of the series of tests are very clear. As the grinding pressure increases, the removal rate increases and the surface quality is remaining constant. From the grinding force of 300 Newton, however, the curve of the removal rate flattens out. There is a risk that my sample material will deform by too high normal forces the grinding process. Therefore, I would limit the maximum grinding pressure to 300 newtons for my chosen sample material. Basically, when changing the grinding forces, it must always be kept in mind that the abrasive pressure is also increasing the plastic deformation in the sample material. These deformations must be removed in the subsequent grinding and polishing steps in order to be able to analyze the true material structure. Therefore, be careful, especially when increasing the grinding pressure. Unfortunately, I did not have the opportunity to measure the direct influence on the material structure through further analysis methods. Here I have created a graph that shows the recommended specific grinding pressure for different material groups. Note that this is only a rough recommendation, as the material properties of your sample material may depend on different alloy components and also on your sample geometry. However, you are welcome to use this graph to check the grinding force of your preparation. To do this, simply calculate the sample area in square millimeters and multiply it by the corresponding specific grinding pressure from the diagram. As a result, you will then receive the recommended grinding force for your sample material. Let's talk about my last test of my series of experiments. In this experiment, I varied the speed of the grinding stone and changed the relative speed between the sample and my abrasive grain. With the QGrind XL, our plane grinding machine, speeds from 1000 to 2000 RPM can be set. In the most preparation methods, the rotation speed of 1500 RPM are chosen for stone grinding and metallography. It is known from the industrial grinding process with grinding stones that the surface quality of the ground workpieces remains constant when the cutting speed changes, but the removal rate can be increased by increasing speed. As you can see in my test results, I was able to confirm this increasing of the removal rate due to the increased cutting speed. At different cutting speeds, the surface quality remains constantly high on a constant level, but the cutting removal rate is increasing. But as I told you before, I'm not able to evaluate the impact to the material structure in my tests. Therefore, the grinding with increased rotation speeds remains a test field for me. At this point, let me briefly summarize my series of experiments and make a conclusion. We have learned that dressing at the right time increases material removal and can avoid deformation and unnecessary heat input. The dressing parameters have a very large influence on the removal rate and the surface quality in the stone grinding process. At high dressing speed, the material can be roughed, while at low dressing speed, a high surface finish is achieved. With our new QGrind XL plane grinding machine, it is possible to combine two different grinding steps, for example, one step in roughing mode and a second step in finishing mode. This can both shorten the grinding time and achieve a high surface quality. In addition, there is a possibility to influence the grinding process through the grinding force and the speed. However, the effect on the material structure must be taken into account. Basically, we can state that plane grinding is used to prepare samples or sample holders for subsequent preparation steps, to remove unwanted material, or to grind samples to a target plane. Plane grinding can be used to process different materials, and there are several ways to optimize the removal rate and the surface finish for specific applications. This can reduce the preparation time, improve preparation quality, and save costs due to lower consumption of consumables. We hope that through this webinar, we were able to introduce you the topic of plane grinding and have inspired you to optimize your preparation methods. If you have any questions, please feel free to contact your contact person at QATM at any time. We would like to thank you for the participation and wish you and your families Merry Christmas and a peaceful New Year.